All right, folks. I would like to discuss some of the things that were in the video on Friday, and then build on that. One of the things that is going to be very, very, very vital for this course is our knowledge about something called an identity. Okay? College algebra, day one, we talked about what identities were. Anybody remember? Okay. So first day of college algebra, we talked about linear equations in regards to identities. But we have three types of equations when we deal with linear equations. Okay? We have ones that are called conditional. It means that they are only true on the condition that I choose the correct x value, essentially. So this is only true on the condition that x is 3, right? Does that make sense? These over here are called contradictions. Okay, so we got conditionals and contradiction. Contradiction means that it is never true. Does that make sense? Okay, when I contradict myself, that means I've negated what I've already said, right? Went against what I've said. Then that's kind of what's going on here. If we multiply things out, do we see that these two lines are parallel? And based on our ideas about how we find solutions in equations graphically, it's the x value of where they intersect, right? Well, if they're parallel, they don't intersect, so that's a contradiction. Our third type of equation is what we call an identity. Okay? An identity is an equation that is always true regardless of the variable input. If I multiply the right-hand side out, you get 2x minus 6, right? You get the same exact thing as the left-hand side. Okay, but if we go back to like algebra 1, and we were doing like in algebra 1, you guys were learning how to solve systems of equations, or you might have been talking about parallel lines and that kind of stuff as well. If I type in 2x minus 6, I get that. If I type in 2 times the quantity x minus 3, is it the same thing? Yes, it is. Okay, so the question is, and because of, in light of what we know about solutions to equations being the x values of where the two sides of the equation intersect, here we're seeing that the two sides of the equation intersect at all x values, right? So regardless of what you plug in for x on the left-hand side and the right-hand side, you're going to get the same quantity. That's what an identity is. Okay, identities are extremely useful and ever present in trigonometry. Okay, we've already talked about a couple. Okay, those reciprocal identities up there. We've talked about how sine and cosecant are reciprocals. Okay, written this way, and there's two different ways you can write these. You can write, so what this one is, the way we phrase this, and this will be useful in our homework and some of these other questions that we do as practice. But right now, we have cosecant written in terms of, or expressed in terms of sine. Does that make sense? This is cosecant expressed in terms of sine, meaning that you have cosecant isolated, and sine is the only trig ratio that I need to identify what cosecant is. Okay? We can also write this as sine of theta is equal to 1 over cosecant of theta. That is expressing sine in terms of cosecant. Okay? And I can generate that red one by taking the black one, multiplying both sides by sine, right? So I multiply both sides by sine, I get sine theta cosecant theta equals 1. And then solve for sine by dividing by cosecant. Okay? But those are reciprocal identities. Okay? And if I were to graph them, okay? Now if I do the cosecant one, these graphs are going to look a little bit different. So do cosecant of x, gives me that right there. Okay, we'll develop an understanding for that in chapter 6. But if I go 1 over sine, is it the same curve? Yeah. So much like we saw with the lines, because these intersect at all x values, that means these are always the same. Those must be an identity. Okay with everybody? Okay. So that's kind of the nice thing. I think you can draw a comparison between what we know about identities with lines, and allows us then to make an understanding. Even though I don't know how to graph either of these things yet, we now see that we have that relationship. So sine looks like this. So if I go 1 divided by then cosecant, gives me the same thing, right? Okay. So however you want to write it, sine equals 1 over cosecant. Those two are equal, then that's a trig identity. All right, these two are equal, trig identity. Okay. My suggestion, and the hope is that maybe you already know what both of them are and you've committed those to memory. I would not memorize both of them. Okay, and I'm going to try to show you. There's a lot of stuff here in this table, and this table can get a lot more detailed. Memorization fails you at some point, whether it's early, whether it's a week from now, 2 weeks from now, 10 years from now. You will forget some of these things. Okay. Last class, I told them once we looked at this one, and we'll get there in a little bit, I asked them to ask me what the other two were, and I couldn't tell them. Okay, because I didn't know them, because I don't memorize them. Okay, I know how they're created from this one. So if I need them, I will create them. Does that make sense? Now, because I used them all last period, I know them. Okay. As you use them, the more frequently you use them, the more they become ingrained and you learn them. Okay. So, at the end of this week, we use those enough, you'll know them. Okay. But this time next year, will you? Because there's probably going to be a gap of time between when we last see them this year and when we need to see them again in calculus. Okay. So you might forget them, but I'm going to show you how to generate them if you do forget them. And that way to generate them is so much easier to remember than what these two things are. Does that kind of make sense? I try to give you guys ways of structuring instead of memorization. I think memorization is terrible. You've heard me say this before. Give you ways to structure your kind of like filing cabinet. It's called schema, like the psychological term for it. But it's like the roadmap or the filing cabinet system that you have in your mind to learn and recall things. Okay, and I think relationships allow us to do that much better than just pure memorization. Does that make sense? Pure memorization would be like everything that I memorize would be like one piece of paper, scanned, printed, and put in my filing cabinet. Would that soon fill my filing cabinet up a lot real fast? Okay. But if I learn a piece of information and connect it to 2 or 3 or 4 other things, now I've got maybe 5 pieces of paper that were in that filing cabinet, and I can put them on maybe an index card. Does that make sense? And now I've got a lot more room in my filing cabinet, but I've got a lot more knowledge as well. Does that make sense? So that's the kind of way I want to try to get you guys to start viewing just education in general. Secant is the reciprocal of cosine. Okay, so you're right, secant theta equals 1 over cosine, and then cotangent is 1 over tangent. Okay. Now these other two down here, we've talked about them, but I think maybe it makes sense to demonstrate why, again, those are the same. Okay. So if we go back to the way we identified trig ratios, we said that sine of theta was equal to y over r, right? And again, y over r is this. If that's theta, this point is xy, that distance is x, that distance is y, and our hypotenuse is r. Remember that? Well, y over r is opposite of our hypotenuse. That's exactly the way that sine is defined. Cosine is x over r. Okay? And tangent is y over x. Okay? Well, if I take these two things right there and divide them, take y over r divided by x over r, what's that turn into? Okay, y over r times r over x. So what happens to the r's? We do y over x, right? Okay, so that y over x is exactly that thing right there, correct? Does that make sense? So let's just keep drawing the conclusions, should you keep going down this line of equality. If y over r divided by x over r is the same as y over x, Now y over x is tangent of theta. Didn't that tangent of theta arrive by y over r, which was sine, divided by x over r, which was cosine? Does that give me that relationship? Does that make sense? Okay. So tangent of theta, if I were to graph this again, okay, let's kind of look at these. So here's sine of theta, or sine of x. Here's cosine of x. Okay? And if I divide those in the right order, do f divided by g, it gives me that. Okay? That's, you see where it says sine over cosine, right? Well, now I'm going to type in tangent of x. Is it the same curve? Yeah. Okay? So it's an identity. These two things I've highlighted here are equivalent to one another at all times. Okay? Now, there are some asymptotes in here, like x equals pi over 2. There's an asymptote there. For the reason, if I'm looking at, just think about this. If you're looking at 90 degrees or pi over 2, so I'm at pi over 2 right there. That's 90 degrees, correct? The x value is 0, the y value is 1, correct? Tangent, then, of theta, or tangent of, let's say, 90 degrees, would equal y over x. Can I take 1 divided by 0? No, so it's undefined. That's why on our graphs down here, at pi over 2, which is equivalent to 90 degrees, we have that vertical asymptote. Is that okay with everybody? All right. There's other places that happens. 3 pi over 2 happens as well. But that's the tangent written in terms of sine and cosine, or expressed in terms of sine and cosine. If the cotangent is the reciprocal of tangent, based off of this argument right here, and we've got another way of identifying tangent as sine over cosine, can't we say cotangent is cosine over sine? Is that the reciprocal of this? Does that make sense to everybody? Okay. So those are 5 identities based off of the reciprocal concept. Does anybody have questions on those? Okay. The next one, okay, it's called a Pythagorean identity. Okay, and the identity is this, and there's some notation here that I think we should probably talk about. If I write sine, I'm going to read this as sine squared theta. Okay? What that means to us is that we've got sine of theta multiplied by sine of theta. Okay? An alternative way of writing that is to write it this way. Sine of theta squared like that. That is telling me sine of theta times sine of theta. Is it okay? Now, the only thing that is different between the right-hand sides that I just wrote is that in the top one, I don't have parentheses around my theta. In the bottom one, I do. Doing things by hand, you usually want to put parentheses around your argument or your angle, which we're calling theta here. But in a lot of textbooks, they don't do that. Okay, especially your more advanced textbooks, they start leaving out a lot of parentheses. Okay, so what happens is that we get to a point where we have something like this. And what that means, or one of the ways that that can be interpreted, is that. And this is not what we want. That is not the same as these two things. Does that make sense? Okay. Now, we're going to write it that way a lot. Okay, but if you're using your TI-83 or 84, you're probably going to have, I know you're going to have to type it in that bottom way. Okay. GeoGebra, I type it in that bottom way, but I think it'll let me type in the top way. And Desmos does let me use either. Okay. It's a lot like this. If I were to say I have like radical 2 times x, if I write it like that, radical 2 times x, is there ambiguity the way that I sloppily wrote that, if that's a word, where x belongs? And even if I say it, radical 2 times x, is it confused on whether x should be underneath the radical or outside? Yeah. But if I write it this way, x radical 2, and I say it that way, does that remove all ambiguity on where that x should be? Yes. Okay. So we developed that notation to alleviate that ambiguity. Same thing here. Okay. Because putting that 2 up here to the upper right hand corner, if I forget parentheses especially, there's ambiguity on what I really want to be squared here. But if I write it as an exponent of the word and then my argument, it eliminates all that ambiguity. And we know it's sine theta times sine theta. Is it okay? All right. So I've been in courses. I've been instructed by, when I was in high school, a teacher that I was never explained by. And it was just, we were supposed to assume that or understand that on our own. I've seen other teachers teach it without ever explaining it, and people get confused. Okay, so what is an identity? So sine squared theta plus cosine squared theta equals 1 is our relationship here. It's called a Pythagorean identity. Let's talk about that over here to the side. So we have sine squared theta plus cosine squared theta equals 1. Let's talk about why that is the case. If I have some theta right there, okay, and I have this to be my point x comma y. So this is x, and that distance is y. We can find this r by taking x squared plus y squared should equal r squared, right? We even had the formula earlier where we defined our trig functions in terms of x, y, and r. We had a formula in the definition that said r was equal to square root of x squared plus y squared. Okay, I need it. Yeah, y squared. I don't know why I did it right. So what we're going to do here is, and I think we mentioned this, if I were to take my terminating ray and just keep rotating it, but tracing that point right there as it rotated, what do I create? Create a circle. Okay? What is the formula for a circle? Okay, and that's a circle centered at 0, 0. So if I write this, x minus h squared plus y minus k squared equals r squared, h and k is your center, r is your radius. Okay, you guys remember talking about conic sections last year? You should have. This is the formula for any circle in the coordinate plane. Okay? Well, if we're centered at 0, 0, that goes to 0 and that goes to 0, and I'm left with x squared plus y squared equals r squared. Does that make sense? Okay? That's the exact same relationship that we're getting over here with this triangle. You all right with that? Okay. Now, if I said that this was theta, didn't we say that the sine of theta was y over r? Didn't we say that cosine of theta was x over r? You guys agree with that? Okay. Let's go ahead and we do a number of things here. Let's just make things a little bit easier. Let's say r is 1. Let's force that. If r is 1, what does this become? Sine of theta just becomes what? Y over 1, right? Cosine theta becomes x over 1, right? So if that's the case, come down here. Okay, so if I choose a point that is on this circle, okay, and this is just because I chose r to be 1. If r was 2, it would be the same. It would be the same relationship because of similar triangles and all that kind of stuff. But if y is sine of theta, then y squared would be sine squared theta. Does that make sense? If cosine is x, then right there, cosine squared should be x squared. R, we said, was 1. So r squared is 1. And we get that. Now I wrote it backwards, but commutative property says you can. So sine squared plus cosine squared equals 1. What does that mean to us? That means no matter what I choose as an angle theta, give me an angle for theta. Give me something that we can work with that's easy. 45. So if that's 45, this would be n. That would be n. This would be n radical 2, right? Okay. So cosine of 45 degrees would be adjacent over hypotenuse, right? I'm just going to write that as radical 2 or 2, if that simplifies. Sine of 45 would be opposite over hypotenuse. Radical 2 or 2, right? Okay. So right now we have, so basically I'm going to ask, okay, well, what is the cosine squared of 45 plus sine squared of 45? What does that equal to? Well, so cosine squared 45, that means cosine of 45 times cosine of 45, right? What was cosine of 45? Radical 2 or 2. So writing that as squared would be that, right? Sine squared of 45 is sine of 45 times sine of 45. Well, sine of 45, radical 2 or 2. What does that equal? What's radical 2 over 2 squared? 1/2. It's 2/4, right? Is this 2/4? What's 2/4 plus 2/4? Right? What if you change that angle? Give me another angle. 30. So n, 2n, n radical 3. So sine of 30, we have said before, sine of 30, n over 2n, which is 1/2, right? Cosine of 30, n radical 3 over 2n, so that turns into radical 3 over 2, correct? Okay. Well, so if I go sine squared of 30 plus cosine squared of 30, what does that equal? Well, sine squared of 30, sine of 30 is 1/2, right? Cosine of 30, radical 3 over 2, what's 1/2 squared? 1/4. What's radical 3/2 squared? 3/4. What's 1/4 plus 3/4? 1. Okay. Now, you're seeing that that's true for 30 and 45, right? It's going to be true for 60. It's going to be true for 150, because the 150 references back to 30, right? 210 references back to 30. 45 references to 135, or 135 references to 45. Also to 225, and also 315. Okay. 30 references to 150, or 30 is a reference for 150, 210, 330. 60 is a reference for 120, 240, and 300. Okay. So I could ask you questions about those multiples of 30, 45, and 60, right? And all of those are going, no matter what I choose, all of those are going to evaluate 1. But what is nice is, what if I say 12.2478? Pretty random value, right? Well, if I square the sine of that and square the cosine of that and add them together, it's going to give me 1. Okay? And this should demonstrate that. We'll do it 2 different ways here. If I type in, so just sine of theta, or sine of x, looks like that. Cosine of x, looks like that. So if I take f of x and I square it, should look like that, blue one. Take g of x and square it, gives me that orange one. Okay, so let's just look at those 2. Take any x value, no matter where you are, okay, and add them together. Okay, that x value right there is 0 plus that x value, or at that x value right there, take that y value is 0, take that y value is 0, add them together, you get 1, right? Take this one here, y value, add together, both those would be 1/2 plus 1/2, gives you 1, right? So when I take the h plus the p, does it give me 1 all the time. Does that make sense? Okay. We can kind of look at this in an evaluation scenario here on Desmos. Okay. I've got cosine squared of A plus sine squared of A equals 1, and then down there I define A, and I'm just letting A oscillate between 0 and 360. And you're seeing there that no matter what value of A that gets plugged in, it still evaluates to 1, right? So because I'm going from 0 to 360, we understand coterminal angles, I can actually make this 360 anything I want. And as we oscillate through, because that angle right there will, if I start subtracting multiples of 360, will get down to something between 0 and 360, right? Okay, so that's coterminal with something. And I can keep doing it. I'm always getting 1 back no matter what my input is. Is it okay? So that is our, I usually refer to that as kind of our fundamental Pythagorean identity. Okay? Call it Pythagorean because this right here is a squared plus b squared equals c squared, right? Or a leg squared plus a leg squared equals your hypotenuse squared. Okay? Now the other two, I can't tell you what they are off the top of my head, but we'll figure them out. Okay? So, learning these other two is a practice of division. What I'm going to do is I'm going to take sine squared theta plus cosine squared theta is equal to 1. And now I'm going to divide, if I divide everything by 1, it's just going to give me the same thing, right? So that's kind of boring. There's two other things up there that I could divide by. I could divide everything by sine squared, or I could divide everything by cosine squared. We're going to have to do both, so let's just choose one. Let's just divide everything by sine squared. So I'm going to divide this by sine squared theta. I'll divide that by sine squared theta. And I'll divide that by sine squared theta. Okay. What is something divided by itself? 1. So that's going to go down to 1. Okay. Now, this next one, I just want to make sure we understand this. Cosine squared means cosine theta times cosine theta, right? Sine squared means sine theta times sine theta, right? Cosine divided by sine right there. What is cosine divided by sine? Careful. It's cotangent. So that's cotangent there. Is this another cotangent? So what's cotangent times cotangent? Cotangent squared. So cosine over sine is cotangent, but because they're both powers of 2, we've got cotangent squared, right? If those powers were differing, that would not be the scenario we have. Okay, we'll have to investigate that later on if those powers are different. But if they're both squared, both to the first, both to the third, both to the fourth, then our result will be whatever that power is as well, cotangent of whatever that power is. Same idea here. 1 over sine squared is 1 over sine theta times 1 over sine theta. Would you guys agree with that? What's 1 over sine? Cosecant. So you see cosecant times cosecant right here, which would be cosecant squared theta. And that then, if you look over here to our table, is that identity right there. Okay? And my thought is, just because, I've been doing this for a lot longer, we'll use that. We'll use that quite a bit. We'll use both those quite a bit. But I don't think we use them enough to memorize them. In addition, if we do memorize them, people are going to transpose them. Okay? Meaning that the tangent squared plus 1 equals secant squared 1, that one in the middle. People often say tangent squared plus 1 equals cosecant squared. Or they'll say cotangent squared plus 1 equals secant squared. They'll interchange the tangent with cotangent or the secant with cosecant, and it messes everything up. Okay? So if I know that I'm going to use it or I need it, so my philosophy is at any time I see secant, cosecant, cotangent, or tangent squared in a problem, that's going to flip a switch and say, I need to talk about one of these Pythagorean identities, but I'm going to go to the side, do some scratch work, and make sure that I know what appropriate identity I'm using. Does that make sense? Okay. So if that's how I develop that one, what do you think I divide by to get the other one? Yeah. So I got sine squared theta plus cosine squared theta equals 1. I'm going to go through and divide everything else by cosine. Cosine squared theta, cosine squared theta, cosine squared theta. What's sine divided by cosine? Tangent. So these are going to go down to tangent squared theta. What's something divided by itself? 1. And what is 1 divided by cosine? Secant. So it's going to be secant squared. And there's your other Pythagorean identity. Yes? This might show up in, let's say, an equation. And if that shows up in an equation, wouldn't it be easier to replace it with 1? Does that kind of make sense? That's one application. There's a lot of, we're just trying to figure out certain relationships. So in a little bit, this will allow me, when we do this example right here, it says sine theta in terms of cosine theta. What that's going to allow me to do is actually, right now we know if theta is 30 degrees, we know based off the right triangle approach that the sine of 30 is 1/2 and the cosine of 30 is radical 3/2. What this will allow me to do is to figure out what cosine is just by knowing that the sine of 30 is 1/2. Does that kind of make sense? So it's just going to allow us to, a lot of them allow us to do calculations a lot quicker, but they'll absolutely be necessary in some equations. They allow us to identify other relationships. What if I did something like this? Is that true? Yeah, all I did is I took this one, and because the addition property of equality exists, meaning I can add opposite of cosine squared theta to both sides and still have a equivalent result, there is another identity. Could I subtracted sine squared from both sides instead? And there's another identity, right? Okay. I could start taking square roots now, and I would get more identities. Does that make sense? So I would say maybe there's, I don't know, maybe a total of like 4 different identities that we could create there. I could start doing the same thing here. You can kind of see them on the board up there on the whiteboard where I started with this one, I subtracted 1 from both sides, got tangent squared equals secant squared minus 1. But there's like 4 identities that stem from that one. And there's maybe 4 more identities that stem from that one, right? So here's my thought. Do you want to remember 12 separate identities? Actually, yeah, 12 separate. Do you want to memorize that? Or would you rather memorize 1? Sine squared theta plus cosine squared theta equals 1. Coupled with division by either sine squared or cosine squared to generate these other 11 or 12. That would be better, right? Okay. So that's kind of how I'm going to approach class. Now, I want to show you something, not to scare you, but there are going to be a lot of identities in this class, and a lot of them stem from those, okay? If we did a quick identity cheat sheet search on Google, you might get something that looks like this, okay? Now this is a truncated sheet, okay? It's pretty short actually. But you would not want to go through and memorize all of those things, would you? Okay. And here's the fear of this, because right now in Trig, obviously we don't know any of those things. We're the first time we're being introduced to them, but by the end of April, middle of May, you will have those, you will understand those. You'll be able to work within them, okay? But then you're going to take June, July, August off, right? You're going to come back for calculus, and we're going to teach calculus in September and October, kind of how calculus builds. And it's not going to be until November that you need these things again inside calculus. What's going to happen in those 5 months between the last time you memorize these and then the next time you need to use them? Your memory is going to do what? It's going to forget. It's going to fail you. Okay? But if we understand relationships, even if your memory does fail you, those relationships can help us get that memory back a little bit quicker. Does that make sense? If you ask anybody, you guys probably don't know anybody taking calculus right now, right? You guys know anybody taking calculus? Anybody taking branch or anything? One of the hardest parts of calculus is there's two kind of branches of types of problems that we use in calculus. Transcendental equations and non-transcendental equations. Non-transcendental equations are kind of like your polynomial equations. Okay, the polynomial aspect of calculus, pretty easy. Okay, that's the non-transcendental. The transcendental version or portion of calculus is when our equations that we're dealing with are logarithmic, they're exponential, they're trigonometric, and trig equations in calculus throw people for a loop. And the reason is because they didn't learn these relationships the best they should have. Okay, so I always think, okay, if I'm learning something and I don't maybe necessarily know why I'm learning it at the moment and how important it is at the moment, I usually don't learn it as well as I should, right? But if you understand that that's going to be something that's going to be very vital to the next course, maybe it changes the way we approach it right now. I'd like to get through this example right here. This is more of I think there's two things going on in this question that are confusing to people. Okay, one is its structure. What does it mean by express sine theta in terms of cosine theta? Okay, because if I don't know what that means, then I could probably come up with two results here, and only one of them is right. Okay, basically they're saying solve either for sine or solve for cosine. If I don't know this terminology, I would solve for the wrong one. It's much like this. If I said express y in terms of x for 2x plus y equals 3. Okay? Now, this problem here that we're doing with the trig, we don't have that for part yet. Okay? But if I give you an equation, 2x plus y equals 3, and I say express y in terms of x, what does that mean? What variable does that tell me to solve for? Express y, so solve for y, in terms of x, meaning x then is the only thing that y is going to be dependent on. Does that make sense? Okay, so express y in terms of x would mean I'm going y equals 3 minus 2x. If I said express x in terms of y, that's completely different, isn't it? Isn't that going to be x equals 3 minus y all over 2? Okay, so if I mess up the order, obviously it's going to mess up my result. Okay, now, when it says in terms of cosine, that means that is the only trigonometric ratio I am allowed to have on the right-hand side of my equation. Okay, so let's think about this. What we're going to do, they don't tell us which, like that equation, I gave you the equation, y, or 2x plus y equals whatever. I gave you that. They're not giving me this. I have to go back up to my identities and choose an identity that incorporates both those, sine and cosine. Okay? I'm going to grab one. I'm going to grab this one. Okay? Don't write this one down yet, because it's wrong. If I take that one, tangent of theta equals sine over cosine. Okay? Can I express sine? Meaning, can you solve for sine in this problem? How would I solve for sine here? Multiply both sides by cosine. And remember, all we're doing here, cosine theta, when I know what theta is, that's just a number, right? Okay, so maybe that's 1/2. If theta was 60, this would be 1/2. So I multiply both sides by 1/2, and that'll cancel. And over here, I'll get cosine theta tangent theta equals sine theta. So I've expressed sine theta, but it's in terms of cosine and tangent. That's a problem, because I only want it in terms of cosine, right? So maybe that was a bad choice. Okay, we could probably, maybe we'll come back tomorrow and fix that using that choice, because you could do it using that choice. The other choice is this. Sine squared theta plus cosine squared theta equals 1. Is that an identity that incorporates both trig ratios that they're interested in? Okay. Solve for which one? Solve for that one. So what are you going to do first? And then what are you going to do? You want to solve for sine. Right now I've got sine squared solve for, right? Take square root. So sine of theta then, square root this side, square root that side. Jimin, if I introduce a radical, what does that mean? Out front? Plus or minus. Okay? So let's talk about what that's doing for us. And we might have to pick up with this discussion tomorrow. And this is going back to Sam's question. What are you using these identities for? Do you know what cosine of 30 is? Radical 3 over 2, right? Let's say that's the only. Let's say I didn't know or have any idea how to find sine of 30. We already know in the back of our mind sine of 30 should be a half, though, right? Okay. But let's say I didn't know that. Can I go ahead and plug this in and go 1 minus, so cosine of 30 would be radical 3 over 2. What's radical 3 over 2 squared? 3/4. 1 minus 3/4 is 1/4, right? What's the square root of 1/4? So this is all plus or minus, right? So it's plus or minus 1/2. But then if I say, okay, well, 30 is in the first quadrant, then I should choose the positive 1/2. So that tells me what sine of 30 is now by just knowing what cosine of 30 was. Does that make sense to everybody? So that's one of our purposes for having identities. The thing about identities and working with them, not always just one direct route to go. Okay, your neighbor might do something completely different and still arrive at the same result. See ya. No new homework.